Okay, welcome to the next video, continuous distributions. So we're moving on past discrete and into continuous. So continuous variables, as I mentioned earlier, can take on any number in a range of values. And the key here to these functions is to realize that area equals probability. So this curve here represents some continuous variable, and all of that area between A and B is the probability that X is between A and B. Okay. So since the area is the probability, there are some important things to mention. Okay, total area equals 1. The probability of X being just any given number is equal to 0. Probability only exists over intervals, right? X cannot equal a number exactly. You can only have interval areas. So that means it doesn't matter if you have less than or equal to. It's the same thing. And since you're doing calculus, if you happen to know the function f of x, then the probability is the integral, the definite integral from a to b of that function. We're not going to deal with functions that much because all of the functions in probability are generally pretty complicated. So we're just going to deal with either simple things that we can do very easily, or the major distributions which have tables of numbers for them. Okay, so a really easy one is the uniform distribution. It's a completely flat distribution. So the function is just a horizontal line. And this indicates that anything in that range is equally likely. So it's a rectangle. And since the total area must be equal to 1, the height of the rectangle must be 1 over b minus a. All right, that guarantees that the area equals 1. So written in f of x notation, it's a horizontal line, so it's just a number between a and b and 0 everywhere else. Okay, so let's try something. Let's say we have x is uniformly distributed between 10 and 15. That symbol, that curved symbol next to x, means is distributed as. So it's saying x is distributed as a uniform distribution between 10 and 15. So it's a rectangle. First, we have to find the height of the rectangle. Since the rectangle has a side of 5, that means the height must be 1/5. And I want to find the probability that x is between 11 and 12.5. And I've gone ahead and highlighted the area for you. So it's just the area of that rectangle. Since the height we know is 0.2, the probability is 0.3. Okay, simple enough. You just got to find the area of the rectangle. Let's do a conditional problem. So the probability that x is greater than 13 given that x is greater than 12, I'm going to highlight the given statement. That's x greater than 12. And then I'm going to highlight the probability statement. And where they overlap is the numerator of the fraction. It's where x is bigger than 13 and bigger than 12, which you can see is just bigger than 13. It's the same thing. So x being bigger than 13 has an area of 0.4. X being bigger than 12 has an area of 0.6. And we're left with a probability of 2/3. Okay, next example. Let's say we have a mixture of two different uniforms. So there's a 40% chance x is between 0 and 20, and that's uniform. And 60% chance x is being between 20 and 100, also uniform. So it's going to look like this. It's two uniform distributions set side by side. And the two rectangles, as the problem states, have areas of 0.4 and 0.6. Okay, so with that in mind, we really need to figure out what the heights of each rectangle are. The height of the 0.4 rectangle is 0.02, and the height of the longer, shorter rectangle is 0.0075. This guarantees that the two rectangles are the correct areas and that we have a total area of 1. Okay, so let's actually do something with this. The probability that x is bigger than 10 but less than 50 is the area that I've shown there. And I'm just going to break it down into two problems. There's two rectangles there, so I'm just going to add the two areas up. Do them separately and add them up. You should get an area of 0.425, and that's the probability. Okay, I'm going to use this as the given statement in a conditional problem. So make a note of that answer. We're going to need it again. So given that x is between 10 and 50, find the probability that x is less than 25. So I already have the given statement highlighted. Now I'm going to highlight x less than or equal to 25. And that middle part where they overlap, that's the and. That's where x is less than 25 and x is between 10 and 50, which is the numerator of the fraction. And the denominator is the answer from before. The numerator is the area between 10 and 25. Anyways, you can figure it out. It's 0.2375. And when it's all said and done, the answer is 0.5588. Okay, moving on to the next one. So this is, for obvious reasons, called a triangular distribution. And triangles are at least simple because they have a fairly easy formula for area, 1/2 base times height. Okay, so the area must equal 1. The base we know is 3, so finding the height is as simple as solving this equation. The height is then 2/3. Okay. So let's go ahead and try not just a simple probability question, but something about percentile, which is quite a bit trickier. I want to find c such that the probability that x is greater than c is 0.1. So c is then, of course, the 90th percentile, because that means 90% of the area is below c, if 10% is above. Okay, so the picture looks like this. There's a number c, and it's going to be over on the right-hand side. And the area that I've highlighted has to equal 0.1. Okay, so we're going to need to figure out the straight lines that make up this triangle. And knowing the height and two pieces, here is the function. Between 0 and 1, the straight line is 2/3 x. And then from 1 to 3, the straight line is 1 minus 1/3 x. Those are the two lines. You should be able to find the equation of two lines given 2 points. Okay, so clearly c is over to the right. And so I'm going to focus entirely on just the right line, the 1 minus 1/3 x. Okay, so I'm going to do this two ways. So looking at the point c, the point above c is 1 minus 1/3 c, plugging c into the line equation. Then the height of that that triangle, it has a base of 3 minus c and a height of 1 minus 1/3 c. So 1/2 base times height is this mess, which turns into a quadratic, which could be solved, and you could find c, but I'd rather not do the quadratic formula. I'm going to try something else. All right. I'm going to define the base of the triangle as d. And using what I know about that straight line, above it, the height of that rectangle must be 1/3 d. If you think about that straight line function, the height must be 1/3 the base. Okay, this is a much easier question to solve then. The area of the triangle is 1/2 d times 1/3 d, and d is then the square root of 0.6, which means that c is 3 minus the square root of 0.6. Okay, so that's how that one works. Okay, another example of a continuous distribution is, this is called an exponential distribution. You see it looks like an exponential function. And it actually has an infinite support. X could be anything between 0 and infinity. But okay, so let's find the probability that x is between 1 and 3, and I've highlighted that area in pink. So if you are good enough at calculus, you could just do the integral. And I'm not going to assume that you're that good at calculus yet, so I'm going to give you a little information about this graph, which is that the probability that x is greater than any given number is e to the minus 0.5 times that number. Okay, so the strategy I'm going to use is I'm going to find the area bigger than 1, and I'm going to subtract from that the area bigger than 3. And what's left over then is going to be the area between 1 and 3. And this is a common trick that we're going to use, especially with other distributions like the normal. So I have the area greater than 1 minus the area greater than 3, and the answer is 0.3834. Okay, so this is an introduction to continuous distributions, and next video is all about a really important continuous distribution called the normal, which we're going to spend a lot of time working with. But check that out.